All right, and yeah, just kind of reiterate for the recording, we're kind of going to go through a little bit of section 44, 45, and 46. We'll kind of see how this kind of goes through. It's a little bit out of order from the curriculum right now, but I think hopefully it'll be make sense to you guys as you go through it and everything. Okay, and again, like all like the you guys already know this at this point, is that all the notebooks I have, they should be up online on the GitHub repo. So if you wanted to look at some of the code, you're like, oh, like if we implement a neural network, we can check it out and do all that stuff. We can, you can check that out. Oh, cool. Hey, Lucy. Awesome. Just in time for us to go over it. So yeah, so we'll go right into like that section 44, 45, 46. Cool. So let me go ahead and share my screen. And okay, and I lost you guys. Where do you guys go? There you are. All right. So yeah, so we're kind of introducing some neural networks. So I'll straight up say is that neural networks are a very, what's it called? Like very hot right now. Like, and I say right now, I mean, there's a lot of useful things that you can do with a neural network. And the reason why you can do these kind of things is basically a neural network, also called a perceptron or perceptron network, is basically, they can generalize to any form or any function that you want. So they're very versatile. They can work for many situations. However, note that a lot of time to perform well on these with a neural network, like kind of like think like back using compared to like a random forest or an SVM or other kind of classification methods, you usually need a little bit more computing power. And that's actually the real reason why neural networks exist right now and using them in data science and machine learning, because they were actually developed, I believe, 1950s is when the idea of the perceptron actually was designed. But it wasn't until relatively recently where we could actually do something with like GPUs and parallelized processing where we can act in big enough data. Turns out you actually need a lot of data in order for the neural network to really understand things. Quote unquote understand. It doesn't really understand, but like for it to learn, the classifications, you actually need a lot of data and you need a lot of parallel processing. And so that's just what we have right now, where we actually have relatively powerful GPUs, computing power, and we have a large amount of data. So neural networks can be really useful in this way. So kind of know that's what you hear a lot of going forward. So I have a few things I'll show a little bit, but let's start off with what is a neural network? What is it going through? So first of all, like I said, a perceptron. So sometimes you also call these perceptron networks. For the most part, people say neural network or a dense, fully connected network. But basically, the idea here is that you have some inputs, x1, x2, x3. You input it, basically you multiply it by some, what they call it, weight. So think of like some coefficient, some number, multiplied this feature, which is also a number. And you pull this in, combine them together, and then outputs out another number. And that number is going to decide on essentially what is this thing. Is it, for example, let's say you're inputting features like like back for our very first project with the housing project, right? On determining, oh no, that's probably not a good example. I'm trying to think of a good example that we just had classification, but let's see here. If you guys just did your machine learning, what's it called? Your machine learning project. So anything with classification, you could say, okay, like have these features come in and say, is it class A? Is it class B? Is it class C? So the classic example is like, you feed in features about, is it a dog or a cat? And these features come in, whatever these arbitrary features are, you combine them together and outputs a number. And let's say if the number is below 0.5, oh, that's a dog. Oh, if it's above 0.5, it's a cat. And that would be equivalent to like what you're doing. So essentially we're trying to abstract the idea of training this network with numbers, essentially. And note that these numbers can be things like different features, like let's say for the cat example, it could be like, does it have whiskers? Does it not have whiskers? This could be a feature in here. More advanced neural networks, such as a convolutional neural net, which we'll talk about in the future, you can actually feed full pixel values and say, okay, like this pixel value, this pixel is a little brighter than normal. And you can combine these pixels together and figure out, is it a dog or a cat? And basically combine these parts in. So it's a very powerful use case. But this right here is your perceptron. And note that I have like 3 different inputs going in. I think this actually came from the curriculum. This will combine together. You can have multiple, hundreds, if not thousands of inputs coming into this one little, what we call this node here. And then putting this one output here. Okay, does that make sense to everyone? Like that concept? All right, and so notice I put like a similarity to linear regression. So the way this mathematically usually looks is essentially, I'm gonna just draw right directly on here. you essentially have this x1 times w1, so that's that first weight, and then this x2 times w2, x3 times w3. And then we usually have, it's not really drawn here, but usually we have this extra factor that's not based on any feature called a bias. And that bias basically just allows you to, there's a few reasons why we have that. Basically, it allows us to have a little extra points in there. So if these are all 0, you still will have some value from B0 here. And so you add these all together, and that will give you this value, some number in here. So this would look something like this value is going to be equal to, so I'm just kind of showing you what that looks like, is x1, or let's say w1 times x1 plus w2 times x2 plus w3 times x3 plus b0, our bias. And that's going to be combined together essentially to form in this node. So note that this looks very similar to like linear regression. And in fact, that's actually what it basically is. It's essentially is linear regression being combined together. We'll do in next few things something called like an activation, where basically we'll scale this number down to essentially between 0 and 1 for most cases. And so this will turn this number, whatever this number is together, we'll turn this into 0 and 1, or between a number between 0 and 1. And that can output, for example, like, is it a dog? So like, you can imagine this output like is dog. And so this value is between 0 and 1. You can imagine that being the percent, be like, how likely is it actually a dog? If that was your output or whatever output going through. Okay. So I just want to emphasize, like, these are just all numbers essentially. They're just being combined together to say, okay, what's the probability of it being a certain class or not? Okay. Any questions so far about how these combine? Okay, so this is like the one piece. And so this by itself is honestly probably not that exciting. It's just one little piece. But what you can do is essentially put them all together and to bring more complexity. So one, I'm just going to show you this, a very simple of like a single perceptron here. So imagine we have like X and Y are like these two different features. So like imagine this is, if I just kind of like rewrote this right here, this would look something like, this would be X. And this is going to be, there's nothing here. And this is going to be Y. And this inside here will be like Z. Okay, so I'm going to run this guy and say, okay, like let's go ahead and say some random number X, some random number Y. Just going to put this in for example. Say, okay, if X plus Y is less than 0.8, so this is a true and false. And we can basically say, okay, let's go ahead and put these random numbers in here. And you can see here, this actually allows us to draw, like remember these are just random numbers, and this is essentially our little neural network here. And then we're having a function here to say, is it true or false? To basically say, is it going to be, you know, a class? Like I said, like if you imagine like 0.05, you can see like there's going to be a different kind of class here. Like you say, oh, if it's less than 0.05, it's a dog. If it's greater than 0.05, it's a cat, or whatever class we're doing. Okay, and you can see here, what's really cool is that this is essentially just making classification. So we can actually imagine drawing a line here now, but without even drawing a line, we actually use these numbers, combining these together, this perceptron essentially, to create like a different classification. So you can imagine like now we actually have something that's creating a line here. And what's cool is that you don't just have to have just X and Y, you can have X1, X2, X3, X4, X5, however many dimensions you have, and build this together, have that many features to determine, you know, what class it is. Okay. Does that make sense? Can you guys see the connection between this guy and this perceptron? Okay. Thumbs up sounds good. Sideways, you're like, oh, I'm not sure. I see some thumbs ups. Okay. So yeah, if there's any questions, just feel free to like, you know, interrupt me and ask. So you can kind of see it's like, okay, like we basically combine these together, say it's less than or equal to 0.8. We can also have some things like a little more complication. So you can see very similar thing where we have a random number generated, right? And say, okay, less than, instead of just less than equal, we can say less than equal than some random number here squared. So we can see like some extra random like parts. So you can have these really complicated looking shapes. So imagine like your data looks like this. You can train it to say, okay, that's the kind of shape I want. And without ever drawing any extra like lines and stuff like this, we can create this kind of like determining these different classifications. So you can imagine like if I were to actually physically draw this out, let me actually go through it. Random numbers might not be the best thing. Let's try like 50, or let's say 20. Oh wait, it's a rand. Yeah, That's okay, I'll just keep it that way. All right, so you can imagine just a number here, and you can imagine if I try to draw like the line around here, the border around here, that'd be really complicated and really difficult to do, right? But in this case, I can actually put it all together. Oh, I see what I did here. This is just a random number in here. But anyway, you can combine these together to build up this class, okay? So I'm trying to emphasize the point that you can make this more and more complex to get more complex kind of like distribution of points. And what's really cool, you can actually combine these perceptrons together. For example, you can see this right here is this one perceptron of taking in one value. You can also have like this one right here. If you look at like, if I were just to circle this by itself and focus on just this line, that's basically the same perceptron we had before. You have 3 inputs and then this output coming out. So you can actually connect these little perceptrons together and build much more complicated parts. So these are called, when we talk about it in this phrase, we're talking about these right here, X1 and X2 and X3. These are all features. This would be our input layer. This would be our next layer called our hidden layer. And then we can have multiple hidden layers and then our output layer. So we can think of it in this terms of saying, okay, we input stuff. It basically does some mathematics on here and pushes forward, basically combining them into multiple parts and then outputting into a single value, essentially. Or in this case, this is outputting to a single value, but this could also output to different values. You can have like an output layer where you have like 4 different classes like this, where you can have these different parts. So the point is that this is a very flexible methodology. You can basically add more layers, take layers out, extend it outward. You'll notice that we went from 3 to 4. You could do things like 3 to 2, like where you can make it grow smaller or bigger and stuff like this. So this is again like what allows neural networks to be very flexible. You can build it very complex. Of course, you might not want it too complex, and we'll talk about the reasons why. Okay. But can you guys see a little bit like how if these numbers kind of get feed in, we imagine doing some different math on these parts, you can kind of combine them and make different, you know, numbers and stuff going forward. That makes sense to people? Okay, so that's kind of like me drawing it out, but as in all things in life, there's better ways to kind of show you guys about this. So I'm gonna go ahead and share this, let's see here. This neural network. So what's really cool, this is called playground.tensorflow.org. So TensorFlow is a package kind of similar to Keras and stuff to build up neural networks. But you can imagine these are kind of like these different features, X1, X2, X3, and you can basically build up these kind of different layers. So this is our first input layer. This is our features. This right here is going to be our hidden layer. So you can see there's 2 different hidden layers, or yeah, 2 different hidden layers, and then our output of saying, oh, is it yellow, is it orange or blue? So you can imagine it's like, okay, saying this feature is going to look for example, is it going, you know, left and right, or is it going up and down? And you can actually see these different amount of data. So if I feed this data, you can say, oh, it looks like this. So it's really cool as we can do something called training. And so don't worry about this part yet, but basically these are all the hyperparameters we can do to adjust it and say, okay, go ahead and push all the numbers through here. So like it takes some training data and pushes it through and sees at the very output how well it does. So if you imagine going just one training, say, okay, how well did it do? It's like, oh, didn't do great, right? You can see like it marked most of these as blue and then all of these as orange, and it got some of these wrong. So it's kind of cool. So you can actually say, okay, let me go ahead and what we call back propagation. We're gonna say, okay, you didn't do very well. Let's go ahead and see how about, like you didn't do very well, here's the error, give it back to the neural network and say, try again, like using that error. And I'll try to use basically create incent, try to figure out a better way to do this. And it'll kind of keep going in this process of what we call forward propagation, which basically is feeding the numbers through here and saying, here's the output. And then we look at the output and say, oh, the output doesn't look very good. Here's where you messed up. And we propagate that backwards. So back propagation, propagate backward, adjusting the little dials and stuff on these like weights. And then we push it forward again. So we kind of do this whole process of like feeding it forward, and then pushing back the error, feeding it forward, pushing back the error, and kind of going, and we get better and better each time. So you notice that if I do this next one, this next epoch, the main thing to watch is this guy right here, of like what changes in color. So you'll notice that this will eventually, when I push it through, this will end up being more orange. And you'll also notice that these lines right here, you'll notice when I hover over it, you can actually see the weights are like 0.29, -1, -0.12. So these are basically the different values that you're doing, basically like me trying to adjust the dials, but this is all done automatically through the mathematics essentially. So if I push it forward, you'll see that now it's like, oh, look, it's kind of getting more blue over on this side. So it's classifying this side as blue. And you'll notice that the weights, the different like thicknesses of the lines are also changing too. So if I keep kind of going forward, you can kind of see a little bit that's going better and better and better. In fact, if I ran this automatically, you can actually see this go over, and you can see it basically is going through a bunch of time, looping over and over and over again until basically it does a pretty decent job. So, and what's really cool is like I could have gone ahead, let's go restart this. I could have added like other extra hidden layers, like more even complicated, kind of like what these will look like, but the output will still be the same. So you can see if I do this kind of going forward, it doesn't do a great job, and then soon enough it starts figuring it out and it does a better job here. And you can do even more complicated patterns. For example, it trying to figure out this thing, it might not be really easy for us to kind of like tell it what to do, but it'll eventually, as we kind of move forward and forward, you can see a little bit. Let's see if it goes through. So this one's going to take a little longer because it's a lot more complicated. But basically, it's trying to figure out a better way to kind of put this in here. And you'll notice it's like, oh, it's not doing that great. And that's where you can add even like more features going forward. But even without adding this more features, you can start seeing it trying. It's trying really hard to figure how to make these different values and stuff going through. But if I added something like new features like this, and then had it try go through, I can add more complexity in here. And basically this does a better and better job saying, oh, if I add more features in here, or sorry, more neurons, essentially, more complexity, it has a better chance of expressing this complexity in here. So you can see now we're actually getting a better and closer approximation of like what this is supposed to look like. And this might take a while. You know, this is where neural networks, you know, essentially have to like know how to train them and how to like put in the right hyperparameters. For example, like this, for example, might not be the right feature. For example, we might need new features in here to put in. And now we can see a little bit restarting it over. Hopefully, I think this might help a little bit. And this is just me just kind of playing around with it. And that's kind of more or less what you'll like do if you were to train like a neural network, is essentially trying to feed it the right stuff for it to figure out on its own. So you can see on the right here, it's kind of cool. So this output of its values, and you can see it's really struggling. It's really trying to figure this complicated structure out. And so you can see it's not always going to be the best example. And you can see all this complexity. I started off with only 2 parts in here, and going further and further out here, it might be really complicated going through. Okay. So anyway, that's kind of like what a neural, I like this kind of thing because you can kind of see a little bit of the process going forward. But essentially what's happening, I want to emphasize again, is that it's pushing these numbers through on this side, seeing what the error is, pushing it backwards, and seeing if it can recorrect, and trying to get it's trying to get a better and better kind of viewpoint. And note that I haven't even tried messing around with these different, what's it called? These different hyperparameters. Okay, and you can see it's getting more and more complicated. If I pause this, you can see it's not quite there, but it's starting to get more of that shape. And essentially that's what the big plus in neural networks is that I didn't have to decide what these weights are. I can decide on the structure of this network, and it will learn it from basically from the mathematics. Okay. Yeah, does anyone have questions? General, I know that's kind of, it's still a lot to kind of take in, but does that kind of give a little bit of picture of like what's going on, at least going from here? Yeah, I see some head nods. So, okay, cool. All right, so then it's like, okay, well, that was really cool. Let's go ahead and try to implement this, right? So what's really nice, like, okay, that looked really complicated, right? It turns out it's not actually as bad as you might think. So just kind of first, I'm going to build it with Keras. So that's what actually we show in, what's it called? The curriculum. And Keras is a pretty popular package. In fact, things like TensorFlow actually uses Keras to, as an API, basically allows you to interact with building network and everything. Oh, I see a chat message. Okay, thank you, Lucy, for letting me know. Okay, but let's see here. Sorry, so we can use Keras to kind of build up this neural network. So note that basically I'm importing NumPy here. I'm also going to import models and layers and optimizers. This allows me to build up my network. So our model is going to be the actual network itself, and the layers are going to build up on parts of this network. Okay, so in this case, I'm just kind of putting in data. So this is not important by itself for the neural network. It's our typical machine learning loading in data. So you can see here, basically, I'm loading in the iris data from sklearn. So a built-in data set. I think we've seen this a few times now from a couple other study groups. But I'm getting our xtrain and our xtests. So basically, just, having a split. In this case, I'm having 0.04, which usually you have a little bit smaller than this, like 0.02. But that's just for us to demonstrate. So I loaded up this data. And if you're wondering, if you look now at, like, for example, xtrain, you can see xtrain is basically just a bunch of different values, and that's based on what features there are. So if I do like, what's it called? Iris features, I believe, feature names. You can see these are different features: sepal length, sepal width. They're about flowers and stuff like that. And then if you notice for ytrain, for example, these are going to be different classes. So note that these are one hot encoded for the class 0, class 1, class 2. So there's 3 different classes that it can possibly be. Okay, so that's what we want to do. So you can imagine doing like a decision tree or a random forest or SVM. You could use different machine learning algorithms to do this part, but we're going to try to build a neural network. So this is where I'm going to build up this neural network. So the first thing I have to do is basically say, okay, we're doing something called a sequential model. So sequential just means that, like you can see, is that we're just going to move the numbers forward. There's other more complicated neural networks you can make, like recurrent neural networks, but we're going to focus on sequential because that's the basics, where we're just moving these numbers through. And so that's why it's called sequential, because we're sequencing them through. So this basically says, all right, we're going to start with a sequential model. Okay, and you'll notice that it's object-oriented programming, so we're making that sequential model as a class. And then we're actually going to build up the network. So now what we can do, we can actually add in different layers. So if you imagine here, this actual network has many layers and nodes. I'm basically saying, okay, we're going to add a layer. So if I actually use this guy here, I'm going to go ahead and refresh this. No, I can't do it that way. So let's imagine like we're building this up for ourselves. Oh wait, what am I doing? There we go. Okay, so imagine we have, let's see, we had 1, 2, 3, we had 4 features, right? So we had like sepal length, sepal width, and I can't remember what the other ones are, but we had 4 different features. So we're going to feed 4 different features, and we're going to add now a dense layer. So that means like a layer right here, and it's going to have 4 units. So not that basically it would be, okay, I add a hidden layer here, and I add 1, 2, 3, 4. So I'll have 4 units here. Okay, and then I'll also add the next layer. So this is going to be the next layer. Note this is comment out here. I'm going to add one with 3 units. So in that case, it's going to be another hidden layer, and I'll have 1, 2, 3. So you can see here, this is essentially what is our neural network's going to look like. You know, that's what we're building. So you can see we start off with 4 features, and then we're going to push it through into 4 neurons, right? And then we're going to feed that into 3 different neurons, and we're going to train it on those points. Okay, do you guys see that similarity? Does that make sense to people? Give me a thumbs up if that's making sense so far. Okay, cool. So just know that basically I built up the structure. Note that I'm kind of skipping over this activation. We're going to kind of ignore that part. But no, this is basically this extra function that says, make sure it's like between 0 and 1 and say like, oh, is this going to be a strong response or a low response? Okay.
But you you arbitrarily picked how many like neurons you wanted, right?
That's right. Yeah. This is like, I could have technically put in like 40.
Right.
Like,
right. Okay.
Like there's not, yeah, no, good point. Note that the only one that had to be done in this case is actually this 4 right here. And it turns out I kind of lied. Yeah, I kind of lied. This is actually a special layer that's going to be the output, since it's going to be 3 different classes. So this has to be 3 because it's going to output either class A, class B, class C. Okay. But if I had more layers, for example, I had that hidden layer right here, I could have put in whatever I wanted in this case. In this case, I put like 16. So just kind of know that there's a couple of things that you have to put in essentially what you're feeding in, but all the things in between, like for example, this units could be 14, this could have been 12, this could have been 2. It's all about kind of just building an arbitrary structure. And certain structures are going to be better, but more or less it's arbitrary. Okay. Good pointing that out, Eric, because that is a good point to make. All right, so note that this one, I'm going to get rid of this guy so it's not too confusing. Basically, I'm having 4 inputs in there. I'm going to use 4 in that hidden layer, and then going to go into the next layer, which is those 3 units, and that will tell us which class it is. So this will basically output say, oh, is it class A, is it class B, and class C? And all these values should be between 0 and 1, okay? So I go ahead and I created this, what's it called, our network and stuff like this. I think I'm getting a little, yeah, I'm getting a little message to say, hey, this thing you're trying to do is deprecated. We don't have to worry about that right now. It just depends what kind of version of TensorFlow or, you know, what's it called, Python you have. So we're just ignore that. And then we say, okay, we can go ahead and compile this model. So what this happens here is, okay, we have this special thing, this model, the structure, and now we're gonna put in basically all these extra hyperparameters, like this optimizer, there's something called the learning rate. We'll talk about that a little bit more. Momentum, and then basically this other optimization part. So just know that basically we're saying, okay, put this together and we're going to determine it through, this is going to be the loss. So you notice that loss equals our loss error, right? So this is going to say, okay, calculate how bad this model is based on this function. In this case, Keras actually gives us a certain kind of function that we can use. For example, categorical cross entropy is pretty typical because here we're just trying to say, hey, what category is this neural network going to output? Okay, makes sense. So again, nothing really happened. Basically, we just built this model. We haven't done anything with it yet. So it's like, okay, cool. We built this model. Now we have to what we call train it or fit it. So when we actually use this model, it's like, okay, right now the model is just essentially like just sitting there. It looks kind of like this. It's not doing anything yet. So what we do with training, what we're going to do, and I'm actually going to make this down to like, let's say 50 just to make sure it doesn't run too far. What we're going to do is we're going to say, okay, go ahead and feed it in this training data. Basically, we're going to push those numbers through. And it says, hey, this is what it should look like. It should look like these points should be classified in this way. And if they don't do well, we're going to say, hey, neural network, you didn't do a very good job. And then push that error backwards. So we back propagate and say, try again. And then it's going to try to adjust a little bit and then try again. Okay. And we're going to do that. This is epochs or epochs. I think in the US, people tend to say epochs. If you're in the UK, you tend to say epochs. I tend to say epochs. That's just the way I was taught. So that's kind of like, I'll use it. But there's no epochs or epochs. It's the same idea. And that means we're just going to do it 50 times going through. So essentially we do one time, push that thing through, see how bad we did, push it backwards. That's one epoch or epoch. And then we do it again, push it forward, see how bad it did, back propagate. That's the second epoch. And we just keep doing that 50 times. Okay. Does that make sense to everyone so far?
So is the runtime longer the more epochs you do?
That's right. Yeah. Because essentially we're doing it over and over again. So if I imagine.
Yeah. And ideally it should get better with the higher number, right?
That's right.
Okay.
And that's because it's actually using gradient descent. And this is where the curriculum talks about back propagation and propagating the error backwards. Gradient descent, the key part of it is figuring out how do we adjust the weights as we push that error back through the neural network. So how do we adjust those weights? That's the gradient descent part. And basically we just keep redoing that over and over again. Okay. Note this last part here, this batch size. So I think the curriculum doesn't mention this too much, but the batch size is kind of an important part, is that sometimes you have a huge amount of data. And if you try to push all, like imagine like trying to, for each of those features and you have like 10, like say 1 million training data points. Well, you'd have to feed basically the first one in there, the second one in there, the third one in there, the fourth one in there, all through all million. And then afterwards say, hey, how bad did it do? Right? It turns out that part's really fast. But if you look at all 1 million points and you say, okay, how bad did you do? Then what you have to do is like, okay, let's push back all of those errors together. So all 1 million errors and say, how do we adjust it so we make it work for 1 million errors or for 1 million data points? And that can take a long time. So one thing you can do is say, okay, let me just send it in a batch. Let me just send a small group of the 1 million ones at a time. Send, let's say, a batch of 50 of them. Send it down the pipe, like down the neural network. See how well it does. It's like, okay, it didn't do very well on these 50. Send it all the way back. And then you adjusted all the weights for those 50s, and that will be one epoch. And then you take a new batch of 50 and do the same process all over again and kind of go through. And the idea here is that way you can train it very quickly without having to look at all of the data points all at once. But eventually the idea is that you would look through all of the data points. Does that make sense? Okay. So yeah, so that's what this batch 16 is saying. I'm going to take 16 at a time versus using the whole data set. In this case, to be honest, I probably could have got rid of the batch size and just used all of the data points because I think there's only 150 total. But I'm just using 16 just to kind of prove a point of like how it goes through. Okay. Cool. So when I run this line now, it will go ahead and try to take this X train and then compare it to its Y train, say what the true labels are supposed to be. And it's going to do this 50 times with like 16 points at a time. So it's going to feed 16 through, propagate that error backwards, try again with 16 more, propagate that error backwards, and it's going to get better and better over time. Okay. So I'm going to go ahead and feed it through, and you'll see, and if this was if I had a larger data set, you'll actually see this kind of go forward like slowly. But you can see here, basically, it's showing me how big the loss is every epoch. So you see the first epoch out of 50, it took 7 milliseconds per step to actually finish through. It took 1 second total, and you can see here the loss was 1.1. Sorry, I'm guessing the numbers, but like this number right here. And then the second time, okay, it says it finishes there and it tries to push that error backwards back to the thing. It's like, okay, try again after it's adjusting all those different weights, and it goes again. And remember, you can see the loss is getting smaller. So that's what we want. We want our loss to get smaller and smaller and smaller. Basically, it's doing better and better. It's getting less errors. And you can see here, after 9, we can actually get smaller and smaller. And you can see here that loss getting smaller and smaller and smaller. And you can see after 50, it's getting pretty decent. We probably could have kept going, but you can see the also diminishing returns. It's not getting that much better after 50. And so then what we can do after kind of looking at this guy, we can go ahead and evaluate and see how well did you do. So this stuff is what we've seen before, but you do the model.evaluate, and this will basically feed back information, say, hey, how well did you do against this test data? So the test data set is something it's never seen before, and it's going to see how well did you perform on this part. Okay. So I guess before I go and evaluate, are there any questions on how this model trained right here? Like what's going on? You sound pretty good? Okay, cool. And we'll come back to this, just gonna mess around. But you can see here, I can say, okay, how well did you do? And basically I can run this right here, and this will tell me some metrics and saying, how well did you do? In this case, it said, oh, you got a 73% accuracy. So that means of the X tests, so this stuff that it's never seen before, it will get a 73% accuracy. Kind of quick check here. If I instead of doing for X test, X train, or for X tests and Y tests, if I instead did X train and Y train, would we expect that accuracy to be smaller? Like we got a 73% accuracy with the test set. Would we expect the train set to do better or worse?
Better.
Better. And why is that?
Because it trained on that data, so it knows it because it's seen it.
That's right. So we would expect it to do better unless random chance, right? And if I run this, we'll probably get something like 90%. And this case, oh, actually not even that much higher, 74%. So we probably could have trained this a little bit longer in that case. But just to kind of show you, it's like, okay, we would expect the test error to be, the accuracy to be lower. So more errors in that test set because it hasn't seen it yet. Okay. So, and then you can see a little bit, it's like, okay, we can see a little bit of like what classes did it predict? We can actually see in this case, this is what it predicts outwards. So remember, it's going to output 3 different parts. This is going to be class 0, class 1, class 2. And these represent, is anyone going to guess like what these rows represent? So this is supposed to be for one data point in X tests. Like what are these numbers representing, you think?
The percentages of what class it thinks it is?
Yeah, it's kind of like the probability it thinks with the classes. If you notice, it'll basically add up to 1 every single time.
Right.
Yeah. So you can see basically it's saying, hey, I think with there's a 40% chance that this is class 1, and there's a 38% chance that this is class 0. Excuse me. As you can see here, like it's like, oh, it's not really, it might be either one of these. It's not really sure, but it's less likely this one. And you can see on this third data point, it really doesn't think it's class 1, but it's pretty sure with nearly 70% probability that it is class 2. Okay, so that's kind of how this is interpreting it. And so when we say, oh, it's going to say it's 0, 1, or 2, it's actually outputting a probability and saying what's the highest probability. Okay, so that's how we determine this part. Say, okay, like, well, we want to see what is it predicts, and not just the probabilities. Like, what do you think it is? What's the most probable one? We can use the argument max, which basically says, of this little row here, which is the highest value. And it'll say, oh, it's giving me the first one, the second one, or the third one. So this allows us to say, okay, instead of just like probabilities, we say, oh, what class is it? In this case, it looks like it never even guesses at class 0. Okay. And then, of course, we can do some other metrics, for example, seeing, for example, the overall, what I have here. Oh, it's just seeing basically, you know, how many times did it get it right. And so this is the overall accuracy afterwards. Okay. So, and note that this wasn't the best one. So let's say, for example, we go back to this, like, okay, let's go ahead and try to do like, I think originally I had like 500 here. So this will take longer. So note that I have a little timing thing here. This took about 1.5 seconds in total to do 50 times. If I run 500, it's not going to do it 500 times. And if I run this now, you can see it's going really quickly. Sorry. There it goes. So you can see it's still going, still going. See if I can kind of drag this down. Yeah, and then it just finished. But you can see the loss is getting much smaller now. So it's doing much better. But even then, you can see at 500, it's about 0.1357 as the loss. But if I go up to here, it's not that much better than 150. And you can see probably about right over here, it's not really getting that much lower even after doing 100 times. So it's got basically diminishing returns. And if we do this now, if we check out the X tests, we're hoping that it took more time. It means that learn more nuance for the neural network. We can hopefully have it higher than, I think it was 0.73 originally. And so this case you can see here is that our loss metrics, oh, like that's pretty good. 0.02 is our actual loss in that case. So that's not bad. So now we can go and try to check out the classes and see how well it performs. And you can see, oh, good, we actually got some zeros now. So before we was just guessing 1 and 2. Now actually kind of got a better idea. And we can see the overall accuracy now, it's about 92%. So much better than we had before. And you can see, you can imagine now we can adjust this, like 500 is probably all we really need, but you can add more like I mentioned over here, is we can have like another neural network. So, okay, let's try it for like another hidden layer. So a little more complexity in this by itself. So if I do this over now, just to kind of show you a little bit, I haven't changed anything other than just adding a new hidden layer. Maybe it'll perform a little bit better. It's going to perform a little bit slower overall. Actually, didn't see how long it took the last time. But it might take a little longer because it's a more complex neural network. And you can see it going by really quickly. It's going to be done in a second. So 11 seconds. So you can see it took a lot longer than it was with 50. And then we can check out our loss metric. So hopefully this is even smaller. And you can see, hey, that's not bad. It's 0.08. So we can see what classes it kind of determined, right? If you look at this a little bit closer, you can see is that most of the values will likely be relatively small. And the reason why this is happening too is that you can see this is like 99%. It's like 99% sure that this is class 0, right? So you can kind of see it's a lot more certain in this round through. And so hopefully this predictions, I might not get it perfectly, right? But hopefully it gets a little better to 92%, say 95%. So you can see it gets better and better with that more complexity. And now I won't kind of go through this, but like if you imagine if you have even more complexity in there, right? What's one of, would we expect if we add more and more complexity, will this number get better and better? I see some nods. Will it definitely get better and better? So what would happen, you think, if I added like a lot of complexity to this with the training model? What do you think would end up happening to this value? So one thing, go ahead, Eric.
No, I don't really know.
Okay, yeah, so one is that you obviously you can only get so good, right? Like if I got 100%, like obviously I can't get any better than 100%, right? But one issue you might come into is that it might overfit. So it might think it's really good at this training set, but it doesn't actually perform very well on the overall testing set. This is a relatively simple data set and so small that what will happen in reality is that this will actually probably end up just memorizing the answers. And when it memorizes the answers, then it's going to be really easy for it to, what's it called? For it to overfit. So remember how this one right here was about 0.08. We would expect this to be a little bit worse. So you can see here, it's doing a little bit more, like it's a little more accurate in that case, like its loss is smaller. And so you can imagine like it's getting lost basically down to perfect. It's not going to do a good job generalizing. So always like looking out for like overfitting. Okay. And that's one thing I will emphasize is that the more complexity you add to any machine learning model, it will tend to do better than it's like more, like it's less complicated, but to a certain point. It'll get so complicated that it starts just memorizing answers, and then it won't perform very well on the testing, even though the training error will be relatively small. Does that make sense to people? Okay. Yeah, it's like, and I think I used this analogy before. It's like equivalent to like, what's it called? If you gave like a test, like a practice test to like a student, like it's like multiple choice, A, B, C, D, you know, like they can choose one of those. Then you give them a practice test. The idea is like you can give them a practice test and then say, oh, you got these ones wrong, try again, you know, and they try to like, you know, figure out the right answer and stuff like that. And eventually they would get better and better. So they'd be ready for the real test that they haven't seen yet. But the other side of this is if someone literally just remembers it's A, it's C, it's D, it's, you know, B or whatever, like for the different answers, and then try to do the real test and just put A, B, D, C, and everything like that, they're not going to do well on that real test versus the practice test because they essentially overfit. They memorize those answers. And that's essentially what happens when we make it too complicated, the model too complex. Okay, cool. Yeah. Any questions on any of neural networks that we've gone through or implementing all this? Okay, yeah, so you can notice that like the biggest part is really just building up, first of all, this structure. Essentially, what does the model look like? And that's what's going on here. We're basically adding in dense layers in here and building up that different structure. And then there's still some hyperparameters here, like this momentum and what we call learning rate, which we'll talk about maybe next time, but no, we can talk about some. But and then saying how many epochs, how long do we train it for? So most of the actual work comes from just these like 4 different cells, if you notice. And once we have these 4 different cells, that's the whole thing. So this is why it's super powerful. It's like, oh, we can build relatively complex models and still have it learn quite a lot, okay? Or do pretty well on like these complicated tasks and stuff like that. Cool. All right. So, so one thing I'll mention. No, I think we'll end it there, unless you guys. The next part I'll probably go into is activation functions and overfitting. So we'll talk about that for next time. I guess tomorrow's study group. We'll talk about like the activation functions and saying, okay, like one thing I kind of skipped over is the fact that on these kind of nodes right here, on these neurons, is that these values become between 0 and 1. Like whatever value it kind of outputs. And the reason why you can do that is you have a function in here called an activation function that says, how much do you like activate this this neuron? Like what's the minimum number for us to like count for the next round kind of deal. And that's why we call this activation function. And it turns out there's a few different kinds we can do. But we'll talk about that in more detail next time, which will lead us into more kind of hyperparameters with like overfitting and optimizations. Okay. Cool. All right. Yeah. So that's kind of all going through. If there's any last questions before I end it here.
Well, I mean, I guess it's kind of simple, but like, where does the name neural network come from? Is that from like, you know, like the brain?
Yeah. Yeah, that's actually where it comes from. So I kind of skipped over this part. You can think of it as, I don't know people's biology background necessarily, but if you remember back maybe from high school biology or something, if you learn about the brain, you have these dendrites, right? Or you have neurons. So we imagine, here I'll kind of draw it out because this might bring up some memories, is that you have this thing called a neuron cell, and it has like this long thing called the axon. So this is like a little cell. And then you have like these little kind of reception parts, and it sends electrical signals down the cell. So it looks kind of like this. And what happens is basically say, okay, like this neuron will like for whatever reason will like other like nerves and stuff will say, hey, go ahead and send an electrical signal. For the record, I am not a biologist, so I might be saying something like slightly wrong, but more or less this. But basically this neuron will take fires, like, okay, like it activates. So it basically sends an electrical signal, and it'll send an electrical signal down to here, Well, at the end of here will be other neurons. So there might be like a neuron like here. There might be another neuron right here. And so you can imagine like this. And what will happen is like when this activates this electrical part, these neurons, these neuron cells will sense this of, hey, like it's been activated. Go ahead and send this electrical signal now. So these will both send an electrical signal. But this neuron might have something where you have two neurons actually connecting to it, like this one and this one. So maybe this one is sends more strongly or activates when either one of these go off. So you say, okay, like these combined together will activate this one. And so the idea here is that you're connecting these groups of neurons, and this essentially allows you to, essentially the idea is that this is how the brain works. It's basically sending different electrical signals down, and that's what determines on basically what the brain tells it what to do. And so the idea is the neural network is kind of emulating a lot of this. It's like, oh, you have a neuron here, and it can connect to like these couple neurons right here. It's like, okay, well, this neuron might not fire unless both of these come through. So you can imagine that's what the weights are. Is like, are they connected or not, or how strongly connected they are? And so that's where the basis idea of where the neural network comes from, is saying, oh, it's similar to how the brain is kind of connected together. Does that make sense, Eric? I'm going through. Cool, yeah. And I realized too, I probably would just show you like what neuron. Okay, there's a picture of the neuron. So you can see the different neurons and stuff like this, and they're connected together. I'm sure you can find something like a neuron, diagram, synapse. I'm not a biologist, so I won't be able to like show you. Let's hear neuron connection. There you go. I guess this is close like this. We're gonna get. You can see basically they're all kind of connected together. This is obviously an artist example, but like you can kind of see like how the neurons are interconnected. So when one fires, the next one will fire over and stuff like that. And that's the kind of the idea of what this neural network is doing. Okay. So this is a good one. I think memory would be good. Here you can kind of see a little bit the idea right here where we have a neuron firing, and these other ones will kind of detect that, electrical signal. Okay. Good question though, because I definitely did skip over a little bit of like why it's called a neural network and everything. But it's based around this. This is where like you people go like, I think sometimes people get really excited and be like, oh, it's just like how a brain works. I'm like, I guess kind of, but not really. Like, there's honestly, like, I know enough biology to know this is a lot more complicated than just simply saying, oh, like send electrical signal 0 or 1. It's more complicated. We have hormones that set these electrical signals on and when they happen and the other parts. So I wouldn't say necessarily, I would say that our neural networks that we're building are literally like the brain. Also, kind of make things a little short, there's not back propagation in like a neural network in a brain. This is kind of like us kind of like using the analogy of a brain to kind of get the idea of how these activate together. But it's still pretty amazing what you can do with a neural network, building it up like this. You can actually do a very complex task and get things that work pretty amazingly. Okay. Cool. Awesome. So I guess I'll stop it here. Yeah. Unless you guys have any other questions. No? Awesome.